There is a moon in our solar system with a thicker atmosphere than Earth's. A moon with rain, with rivers, with lakes, with weather systems, with seasons, with dunes shaped by wind, with shorelines that stretch for hundreds of kilometers along the edges of bodies of liquid that are wider than the Caspian Sea. A moon whose surface pressure you could stand in without a pressurized suit, whose sky you could look up at without your eyeballs boiling in their sockets, whose gravity is gentle enough that if you jumped, you would rise slowly, hang for a moment longer than any athlete on Earth ever has, and drift back down like a leaf falling in still air. That moon is Titan. It orbits Saturn. It is the second largest moon in the solar system. It is larger and it is, by virtually every measure that planetary scientists use to rank places as interesting, one of the most extraordinary objects in the known universe. There is just one problem. One problem that is so severe, so fundamental, so deeply woven into the physical reality of Titan, that everything else, every compelling advantage, every breathable pressure, every navigable river, every thick protective atmosphere, collapses against it like paper against a wall. The temperature. Titan's surface temperature hovers around negative 179 degrees Celsius, negative 290 degrees Fahrenheit. That is 94 Kelvin above absolute zero. The coldest temperature ever recorded on Earth's surface was negative 89 degrees Celsius at the Soviet Vostok station in Antarctica in 1983. Titan is 90 degrees colder than that. It is cold enough that water ice is not a fragile thing, a temporary state between liquid and vapor, the way we know it on Earth. On Titan, water ice is rock, structural, geological material. The mountains are made of it. The ground is made of it. What flows in Titan's rivers and collects in Titan's lakes is not water. It is liquid methane. Liquid ethane. Hydrocarbons that on Earth exist only as industrial gases, as the fuel in your stove, as the raw material of plastics and synthetic rubber, as a thing you would never consider drinking or swimming in, or building a civilization beside. And yet, here we are, asking the question. Here we are, working through it honestly, refusing to round down the numbers or make them comfortable, because the question of how long humans could survive on Titan is not just a survival exercise. It is a lens through which to understand what Titan actually is, what the limits of human biology actually are, what the engineering constraints of surviving in the outer solar system actually look like, and what it would mean, in the most serious and concrete possible sense, for our species to one day stand on a world that orbits not the sun we know, but the faint pale disk of it, reduced to 1% of its familiar brightness, hanging above an orange sky. If you enjoy videos that take the most extreme questions in planetary science and work through them completely, that never reassure you with vague optimism, but instead sit with the actual numbers and let them mean something, I genuinely appreciate it if you hit the like button and subscribe. It helps more than you know. Now settle in. Let's begin. Before we can answer how long a human could survive on Titan, we need to understand what Titan actually is. Not the thumbnail version, not the single sentence summary, the real thing. Because Titan is strange in ways that are worth dwelling on, and its strangeness is precisely what makes the survival question so interesting. Titan was discovered by the Dutch astronomer Christiaan Huygens on March 25, 1655. He was observing Saturn through a telescope he had built himself, and he noticed a small point of light that moved in a consistent way around the planet. He called it, at first, simply Saturni Luna, the moon of Saturn. It was the first of Saturn's moons ever identified, and for more than 2 centuries, it was thought to be the largest moon in the solar system. We now know that Jupiter's Ganymede is slightly larger, but only slightly. Titan's diameter is 5,149 kilometers. Mercury, the innermost planet, the planet that orbits the Sun in 88 days and has been baked and bombarded for 4.5 billion years, has a diameter of 4,879 kilometers. Titan is bigger than a planet. It just happens to orbit one. The first indication that Titan was genuinely extraordinary came in 1944 when the Spanish-American astronomer Gerard Kuiper detected the spectroscopic signature of methane in Titan's atmosphere. This was the first confirmation that any moon in the solar system had an atmosphere at all. But it wasn't until the Voyager 1 flyby in November 1980 that scientists got their first real look at Titan as a world. What Voyager sent back was, in one sense, deeply frustrating, a featureless orange ball. The atmosphere was so thick, so laden with photochemical haze, that the surface was completely invisible to Voyager's cameras. Titan was a tantalizing mystery, wrapped in an opaque orange shell. The mystery deepened for 2 more decades. Then, in 2004, the Cassini spacecraft arrived at Saturn, and with it came the Huygens probe, built by the European Space Agency, designed for one purpose: to descend through Titan's atmosphere and land on its surface. On January 14, 2005, Huygens entered Titan's atmosphere at around 6 kilometers per second. Over the course of approximately 2.5 hours, it parachuted down through layers of orange haze, transmitting data the entire way. It photographed drainage channels carved by liquid methane. It measured wind speeds and temperatures at every altitude. It detected complex organic molecules in the atmosphere, dozens of them, some of which are precursors to the chemistry of life as we understand it. And then it landed. It came to rest on a surface described by mission scientists as similar to crème brûlée, a thin solid crust over a slightly softer substrate. It kept transmitting from the surface for 72 minutes before Cassini moved below the horizon and the relay link was lost. The Huygens probe is still on Titan. It is still there right now, somewhere on the surface of a moon 1.2 billion kilometers from where you are sitting, in the cold and the dark, with its battery long dead and its cameras long silent. What Huygens and Cassini together revealed was a world of staggering complexity, a world that has, in the most remarkable way, reinvented processes that we consider unique to Earth, using completely different chemistry. Where Earth has a water cycle, evaporation, clouds, rain, rivers, lakes, oceans, Titan has a methane cycle. Methane evaporates from the surface, rises, condenses into clouds, falls as rain, flows into rivers, collects in lakes and seas. Titan's largest body of liquid, Kraken Mare, covers an area of approximately 400,000 square kilometers. That is larger than the Caspian Sea and the Black Sea combined. It is not water. It is a mixture of liquid methane and liquid ethane at a temperature of negative 179 degrees Celsius, under a pressure roughly equal to 1.5 times Earth's atmospheric pressure at sea level. The atmosphere itself is 95% nitrogen, which is actually more similar to Earth's atmospheric composition, which is 78% nitrogen, than any other body in the solar system. The remaining 5% is mostly methane, with trace amounts of hydrogen, ethane, acetylene, propylene, and a bewildering array of more complex organic molecules. The haze particles that make Titan's sky orange are called tholins, a word coined by the astronomer Carl Sagan from the Greek word for muddy. Tholins are complex organic molecules produced when simple molecules like nitrogen and methane are broken apart by ultraviolet radiation and reassembled into longer chains. They coat Titan's surface in a reddish-brown organic gunk. They drift down from the upper atmosphere like a perpetual slow-motion snowfall of chemistry. Titan's gravity is 0.14 grams. For every unit of gravitational force you feel on Earth, you would feel 0.14 units on Titan. You would weigh roughly 117.14 is a 5. Killing Titus with the civilizations of Titan can be heavily done. If you weigh 70 kilograms on Earth, you would weigh about 10 kilograms on Titan. A 2-meter vertical jump on Earth corresponds to roughly a 14-meter jump on Titan. In low gravity, with a thick atmosphere and low terminal velocity, human-powered flight, strapping wings to your arms in flapping, is, at least in principle, physically possible on Titan, in a way it never could be on Earth. Titan orbits Saturn at a distance of approximately 1.2 million kilometers, completing one orbit every 15.9 Earth days. It is tidally locked to Saturn, the same face always pointing toward the planet, the same way our moon always shows the same face to Earth. Saturn looms in Titan's sky, enormous, banded, ringed, visible as a disk rather than a point of light, spanning roughly 5 degrees of arc as seen from Titan's surface, about 10 times the apparent size of the full moon as seen from Earth. On a clear day on Titan, which is never truly clear because the haze is always present, Saturn would be visible as a pale tan disk crossing the sky, its rings tilted at whatever angle the orbital geometry happened to dictate. Titan is, in summary, the most complex moon in the solar system, the only moon with a substantial atmosphere, the only world other than Earth with stable liquid on its surface, a place of rivers and rain and seasons and organic chemistry, and somewhere, possibly, the preconditions for a form of chemistry that might shade into biology. Scientists have speculated, carefully and conservatively, about the possibility of life on Titan. Not life as we know it, not life based on liquid water, but life based on liquid methane, using acetylene as an energy source instead of sunlight, exhaling hydrogen instead of carbon dioxide. No evidence for such life has been found, but the chemistry is there, the precursors are there. And in the long history of this solar system, 4.5 billion years of Titan existing, it would be extraordinary if nothing had ever happened. This is the world we are asking about. This is the world we are imagining a human being standing on. Now let us work through what would actually happen. Let us begin at the bottom of the ladder. No suit, no equipment, no preparation. A human being in ordinary clothing teleported instantaneously to the surface of Titan. What happens? The first thing you would notice, if you had time to notice anything, is the cold. Not as a gradual chill, not as the uncomfortable sensation of walking outside on a winter morning without a coat. As an immediate and catastrophic insult to every cell in your body simultaneously. At negative 179 degrees Celsius, the rate of heat transfer from your body to the surrounding environment would be roughly comparable to plunging into liquid nitrogen. The temperature difference between your body core, 37 degrees Celsius, and the surrounding air is 216 degrees. In comparison, the temperature difference between your body and freezing water is 37 degrees, cold enough to cause death from hypothermia in minutes. The temperature difference between your body and Titan's atmosphere is nearly 6 times greater than that. Exposed skin would begin experiencing frostbite, not in minutes but in seconds. The extremities, fingers, toes, ears, nose, would see ice crystal formation in the tissues within seconds of exposure. Nerve conduction, the electrical signaling that allows pain to be felt, would begin to fail almost immediately as the electrical properties of nerve membranes become compromised in extreme cold. This means the cold would rapidly become painless, which is not a mercy, but a sign of tissue death. The air itself presents a second problem. It contains no oxygen. Titan's atmosphere is 95% nitrogen and approximately 5% methane, with trace amounts of hydrogen and various hydrocarbons. There is no oxygen, none. Breathing Titan's atmosphere is not like breathing thin mountain air, where there is still oxygen but less of it. It is like being in a room that has been completely purged of oxygen and filled with nitrogen, the consequence of which is not a gradual suffocation, not the air running out sensation of holding your breath, but rapid, unconscious collapse. When you breathe pure nitrogen, the body does not register the absence of oxygen in any familiar way. The sensation of needing to breathe is caused by rising carbon dioxide levels in the blood, not by falling oxygen levels. In an atmosphere of pure nitrogen, oxygen drops rapidly in the blood and brain, without the carbon dioxide signal rising commensurately. You do not feel the need to breathe harder. You do not feel distress. You feel, if anything, a brief lightheadedness, and then nothing, as consciousness simply ceases. This process takes between 10 and 20 seconds. So we have two simultaneous killers arriving at the same moment: catastrophic cold and immediate anoxia. The question of which one kills you first is somewhat academic, because neither gives you more than a few tens of seconds of survival in any meaningful sense of that word. The cold would produce rapid cellular damage. The lack of oxygen would produce loss of consciousness within seconds. Death, from the cessation of brain function, would follow within minutes. Though the specific timeline is complicated by the fact that extreme cold simultaneously slows metabolic processes, including those that cause death. An unprotected human on Titan's surface would be dead, or functionally dead in the sense of permanent brain damage, within somewhere between 15 seconds and 2 minutes. Let's call it a minute as a round number that captures the essential truth. An unprotected human on Titan lasts approximately as long as an unprotected human in liquid nitrogen, which is to say, not long at all. This is the flaw of our exploration. Everything that follows is an attempt to build above it. The obvious first step up from the flaw is a spacesuit. If you can seal a human inside a pressurized, temperature-controlled, oxygen-supplying enclosure, you can survive on Titan for as long as the suit systems hold out. This is true in principle. The details are interesting. The first thing to understand is that surviving on Titan in a suit is easier in some ways than surviving on the Moon or on Mars, and dramatically harder in others. On the Moon, the biggest threats are vacuum and radiation. The Moon has no atmosphere, which means a suit must maintain internal pressure against absolute vacuum, while also providing complete protection from solar ultraviolet radiation, solar flares, and the constant bombardment of micrometeorites. The Moon's surface temperature ranges from 127 degrees Celsius in sunlight to negative 173 degrees in shadow, a swing of 300 degrees across the lunar day. Suits for the Moon are extraordinarily complex precisely because the Moon offers nothing. It provides no pressure, no radiation shielding, no thermal moderation. Titan, in contrast, has an atmosphere at 1.45 times Earth's sea level pressure. It has a thick haze layer that absorbs most ultraviolet radiation before it reaches the surface. It has no significant magnetic field of its own, but Saturn's magnetosphere provides substantial protection from charged particle radiation. The surface temperature, while brutally cold, is at least consistent, negative 179 degrees everywhere, all the time, rather than swinging hundreds of degrees depending on whether you are in sunlight or shadow. This means that a suit for Titan does not need to manage vacuum. It does not need to be fully pressurized against zero external pressure. It does not need a rigid structure to hold internal pressure against the void. What it needs, above everything else, is thermal insulation. Extraordinary, relentless, highly engineered thermal insulation. The thermal engineering challenge is this. A human body at rest generates approximately 80 to 100 watts of metabolic heat. During moderate exertion, that rises to 300 to 500 watts. This heat must be kept inside the suit, or more precisely, must be managed so that heat flows out of the suit at exactly the rate the body produces it, maintaining a comfortable internal temperature against a surrounding environment that is 216 degrees colder than your core temperature. The insulation required to achieve this is not trivially thin. Modern spacesuits use multiple layers of radiation reflective insulation, called multi-layer insulation or MLI, interspersed with vacuum gaps. This works extraordinarily well in the vacuum of space, where heat transfer by conduction and convection is essentially zero and the only mechanism is radiation. But Titan does not offer a vacuum. Titan has a thick, dense atmosphere. In a thick atmosphere, heat transfer by convection and conduction is significant. The insulation that works in space does not work the same way in Titan's nitrogen-methane air. Engineers have done calculations on this. The consensus is that a Titan suit would require a rigid outer structure, not the flexible garment of a lunar EVA suit, to accommodate the necessary insulation thickness. Proposals vary, but a plausible design involves aerogel insulation, the lightest solid material ever made, composed of 99.8% air, with extraordinarily low thermal conductivity, sandwiched between layers of aluminized film. The total insulation package might be 5 to 10 centimeters thick, giving the suit an appearance more like an inflatable diver's dry suit than a traditional spacesuit. Some design proposals look more like a powered exoskeleton than a suit. The oxygen supply is the second critical system. Titan's atmosphere contains no oxygen, so the suit must carry it. A human at rest consumes approximately 0.2 litres of oxygen per minute, or about 300 litres per day. A person engaging in moderate physical activity consumes roughly twice that. Standard technical diving equipment, a self-contained breathing apparatus essentially, can supply roughly 200 litres of oxygen from a 12-litre cylinder at 200 bar pressure. For a full day of activity on Titan, you would need a substantial oxygen supply, either as compressed gas or as a chemical oxygen generator. A 12-hour EVA might require a backpack-mounted system weighing 15 to 20 kilograms. Battery life presents the third constraint. The heating systems required to maintain a livable temperature inside the suit, and you would need active heating, not just passive insulation. To replace the heat lost through the suit walls over a long excursion, would consume power continuously. Estimates for the power consumption of a Titan suit's heating system run from 100 to 500 watts, depending on insulation quality and activity level. A 12-hour EVA at 200 watts average consumption requires 2.4 kilowatt-hours of energy. Lithium battery systems that can deliver this while fitting within a practical backpack weight exist today, but they would represent a significant fraction of the suit's total mass. There is also the question of mobility. Titan's low gravity makes movement easier in one sense. Carrying things requires less effort. But the thick suit, the heavy insulation, and the backpack-mounted life support systems add their own inertia. Early astronauts on the Moon found their suits limiting, despite the low lunar gravity. A Titan suit, likely thicker and more rigid, would present similar challenges. Dexterity, the ability to pick things up, manipulate instruments, take samples, would be substantially limited. Given a well-engineered suit with optimized insulation, a well-designed oxygen supply, and sufficient battery capacity, a human on Titan could survive a single extravehicular excursion of roughly 8 to 12 hours. Not indefinitely, not a day. 8 to 12 hours, after which the oxygen supply would need replenishment, the batteries would need recharging, and the astronaut would need warmth and rest. A single suited excursion on Titan. That is the second rung of the ladder. Before we go further up the ladder, it is worth pausing to understand what it actually takes to get to Titan. Because the isolation of Titan is not merely a matter of distance. It is a matter of time, of propulsion, and of the staggering logistics of keeping a human alive across the outer solar system. Titan orbits Saturn at a distance of about 1.2 billion kilometers from the Sun. Earth orbits at 150 million kilometers. The distance from Earth to Titan, depending on orbital positions, varies from roughly 1.2 billion to 1.7 billion kilometers. The Cassini spacecraft, launched in 1997, took 6 years and 9 months to reach Saturn, using gravity assists from Venus twice, Earth once, and Jupiter once to build up the speed needed for the outer solar system. Even with advanced propulsion systems significantly beyond what we currently operate, a human mission to Titan would require a transit time of at least 2 to 3 years each way. That means 2 to 3 years of confinement in a spacecraft before the crew even arrives at Titan. 2 to 3 years of microgravity, which causes bone density loss at approximately 1 to 2% per month, muscle atrophy, cardiovascular deconditioning, fluid shifts toward the head, and immune system changes that are still not fully characterized. 2 to 3 years of radiation exposure from galactic cosmic rays and solar particle events, not fully shielded by any practical spacecraft design. 2 to 3 years of psychological confinement in a small volume with a small number of people, with communication delays to Earth that would make anything like real-time conversation impossible. A communication delay alone is worth pausing on. At the speed of light, a signal from Titan takes between 68 and 84 minutes to reach Earth, depending on orbital positions. A question sent from Titan would receive its response, at minimum, 2 hours and 16 minutes later. For a medical emergency, this is catastrophic. For a navigation crisis, this is catastrophic. For daily human interaction with loved ones and colleagues on Earth, this is deeply isolating. The crew on a Titan mission would be functionally alone. Not in the sense of romantically alone, in the philosophical sense, in the operational sense. Every decision, every crisis, every problem would need to be solved on-site by the crew, without meaningful real-time support from Earth. They would have to carry Earth's knowledge with them, in the form of databases and training, because they could not ask Earth for help in any timely way. The return journey would be equally long. A Titan mission would not be a brief sortie. It would be, at minimum, a mission of 7 to 10 years, from departure to return, with 2 to 4 years spent in the Titan system itself. By comparison, the longest single human spaceflight on record is approximately 437 days, achieved by Russian cosmonaut Valery Polyakov aboard Mir in 1994 to 1995. The longest continuous human presence in space is represented by the International Space Station, where astronauts rotate through 6-month missions. A Titan mission would require duration in space 4 to 6 times longer than any mission ever attempted. The supplies required for such a mission are staggering. A human being consumes approximately 0.85 kilograms of food per day in space, slightly more on a planetary surface where activity levels are higher. 0.85 kilograms per day for 10 years for a crew of, say, 4 astronauts is approximately 12,400 kilograms of food. With packaging and storage, probably 15,000 to 20,000 kilograms. Water can be recycled in space, with current ISS systems recovering approximately 93% of urine and moisture from cabin air, but the remaining 7% must be resupplied. And the recycling systems themselves have mass and maintenance requirements. Oxygen can be produced by electrolysis of water, which requires electrical power, which requires a power supply, which has mass. Every kilogram of supplies sent to Titan must first be launched from Earth against Earth's gravity well, then accelerated to interplanetary velocity, then decelerated into Saturn orbit, then maneuvered into Titan orbit, or descent trajectory. The energy cost of this chain is enormous. Getting 1 kilogram of anything to Titan's surface currently costs, in terms of launch mass, somewhere between 100 and 500 kilograms of rocket propellant, depending on the mission architecture. The logistics are a problem orders of magnitude more complex than anything attempted in human spaceflight history. We are not going to Titan next year. We are probably not going to Titan in the next 50 years with crew. But the question is not when. The question is what it would look like if we did, and whether once we got there, we could survive. So let us proceed up the ladder and assume we have found a way to get there. The next rung of the ladder is a habitat, not a spacesuit, not a brief excursion, an enclosed structure on Titan's surface, pressurized, heated, supplied with oxygen and food, in which humans can live for an extended period. A structure that solves the thermal and atmospheric problems, not temporarily, for 8 to 12 hours, but persistently, for days, weeks, or months. This is, in principle, a solvable engineering problem. More solvable, actually, than a habitat on the Moon or on Mars, for several reasons that are worth spelling out. First, the atmospheric pressure. Titan's surface pressure is 1.45 atmospheres. This means that a Titan habitat does not need to be a pressure vessel in the same sense that a space station is a pressure vessel. On the ISS, the internal pressure is maintained against the absolute vacuum of space, a pressure difference of 1 atmosphere, roughly 14.7 pounds per square inch, acting on every square centimetre of the station's hull. This requires the hull to be genuinely airtight and structurally strong. On Titan, a habitat pressurized to Earth normal conditions at 1 atmosphere would be at 0.45 atmospheres below the external pressure. The pressure will be trying to crush the habitat inward slightly, not explode it outward. This is actually structurally easier to manage than a standard vacuum pressure vessel. Second, radiation. Titan's thick atmosphere and Saturn's magnetic field provide substantially better radiation shielding than the Moon or Mars offers. On the Moon, radiation shielding requires mass, thick layers of regolith piled over habitats or thick-walled structures. On Mars, The thin atmosphere provides some protection but not enough for long-duration habitation without supplemental shielding. On Titan, the natural environment provides considerably more protection. Measurements from the Cassini mission suggest that the radiation dose on Titan's surface is roughly 4 to 5 times the annual dose from natural background radiation on Earth. Elevated, but within ranges that humans can tolerate for extended periods without catastrophic health consequences. Third, construction material. Titan's surface is covered in water ice, organics, and various hydrocarbon compounds. Water ice, if it can be melted and resolidified in useful shapes, is a structural material. Organic compounds on Titan's surface could potentially be processed into polymers or other useful chemical feedstocks with the right chemistry and energy inputs. A habitat in the long run does not necessarily need to import all its structural materials. It might be able to use what is available. The thermal engineering of a Titan habitat is the central challenge. A structure sitting on Titan's surface loses heat to the environment through 3 pathways: radiation, conduction, and convection. Radiation is significant at any temperature. Conduction through the structure's walls and through the ground contact is significant because of the enormous temperature difference. Convection in Titan's dense atmosphere, the movement of cold air around the structure, is potentially the most significant of all. A practical Titan habitat would need insulation. Values comparable to the best industrial cryogenic storage systems, the kind of insulation used to keep liquid hydrogen or liquid helium cold. Multi-layer vacuum insulation is not practical in Titan's atmosphere, but aerogel composites, expanded foam insulation with low thermal conductivity, and vacuum jacket panels, where technically feasible, could combine to provide an insulation system that limits heat loss to manageable levels. The power required to heat the interior of a small habitat, say a 50 cubic meter living space, against Titan's temperature in a well-insulated structure might be on the order of 2 to 5 kilohertz, continuously, every hour of every day. 5 kilohertz continuously. Over a year, that is 43,800 kilohertz of energy. For comparison, the average American household consumes about 10,500 kilohertz of energy per year of electrical energy. A Titan habitat's heating bill alone is 4 American households' worth of electricity, and that is only the heating. Life support, lighting, computers, communications, laboratory equipment, cooking, and all the other electrical demands of a functioning human outpost add perhaps another 2 to 5 kilohertz. The total electrical power demand of a minimal Titan habitat runs to 5 to 10 kilohertz continuously, with no interruption. Where does the power come from? This is one of the most critical questions in any serious discussion of Titan habitation, and the answer is not solar power. At Titan's distance from the Sun, the solar flux, the amount of solar energy arriving per square meter per second, is approximately 1% of what reaches Earth's surface. At Earth's surface, solar panels produce roughly 150 to 200 watts per square meter. At Titan, the same panels would produce 1.5 to 2 watts per square meter, and that assumes clear sky conditions, which Titan never offers because of its perpetual haze. The actual light level on Titan's surface is roughly comparable to a heavily overcast winter day in Scandinavia, but 50 times dimmer. Solar power is not a viable primary energy source for Titan. The serious proposals converge on nuclear power. Specifically, radioisotope thermoelectric generators, RTGs, of the kind that powered the Voyager probes, the Cassini spacecraft, and a Curiosity and Perseverance Mars rovers. An RTG uses the natural decay of a radioactive material, typically plutonium-2038, to generate heat, which is then converted to electricity by thermoelectric elements. An RTG produces power continuously, without sunlight, without moving parts, for decades. The RTGs powering the Voyager probes, launched in 1977, are still producing power today, more than 47 years later, though at reduced output as the plutonium-238 decays. The RTG that powered Cassini produced approximately 880 watts of electrical power at launch, declining to about 670 watts by the end of the mission. A Titan habitat requiring 10 kHz of continuous power would need roughly 15 Cassini-class RTGs. The plutonium-238 required for 15 such RTGs is approximately 2 to 3 kilograms. Plutonium-2038 is extraordinarily rare. The United States had largely stopped producing it after the Cold War and restarted production at a rate of about 400 to 500 grams per year by the 2010s. Scaling this up to produce the quantity needed for a Titan mission is a matter of political will and industrial investment, not fundamental physics. More powerful nuclear systems, actual fission reactors rather than RTGs, have been developed for space applications. The Kilopower project at MESA demonstrated a small fission reactor capable of producing 10 kHz of electrical power from a system weighing less than 1,500 kilograms. A reactor of this class, or a scaled-up version of it, would comfortably provide the power needs of a Titan habitat. The radiation shielding requirements for crew safety near a fission reactor add mass, but are manageable in the context of a surface habitat where the reactor can be physically separated from the living quarters by distance and by regolith shielding. With adequate nuclear power, a Titan habitat can be heated. With heating, it can be livable. With oxygen generation by electrolysis of any available water, the breathing problem can be solved. With supplies launched from Earth, the food problem can be solved in the short term. A crew in a well-powered, well-insulated habitat on Titan's surface could survive for weeks, then months, limited initially by the supply of consumables brought from Earth. The first week in such a habitat would be extraordinary. Not pleasant in a spa vacation sense. Extraordinary in the sense of being surrounded by something unlike anything any human has ever experienced. The sky outside, visible through thick, heavily insulated windows, is a permanent amber orange, the colour of an overcast day filtered through a bottle of pale whiskey. The light is dim, perhaps 1/100th of what you would see on an overcast day in London in November. The ground is brown and reddish, coated in organic compounds that descended from the upper atmosphere over billions of years. In the distance, if the topography cooperates, there might be dunes. Titan has extensive dune fields, made not of sand, but of particles of organic material, shaped by the wind into ridges that can stretch for hundreds of kilometers. The wind itself is light at the surface, typically a few kilometers per hour, though higher in storms. In Titan's dense atmosphere, even a gentle wind carries substantial momentum. 1 kilometer per hour wind on Titan carries roughly 4 times the kinetic energy of the same speed wind on Earth, because air density is approximately 4 times greater. Saturn, if it is in the sky, is a wonder. 5 times the apparent diameter of the full moon is seen from Earth, banded in pale yellows and tans. The rings tilted according to the season. Titan has seasons, as Saturn's 29.5-year orbit around the Sun takes it through axial inclinations that produce a Titanian year of approximately 30 Earth years, with each season lasting about 7 years. The Cassini mission observed Titan in northern winter and spring, watching the northern polar region transition from the enormous North Polar Lake District to a more active, rain-lashed landscape as the methane cycle shifted with the season. In the first week, the crew would be occupied with habitat systems checks, equipment setup, scientific instrument calibration, and the 100 details of establishing a working base. They would conduct short-suited excursions to examine the immediate surface, collect samples, take measurements. They would eat food brought from Earth, sleep in bunks inside the heated module, exercise in the limited space available to counteract the effects of Titan's low gravity on their bones and muscles. Low gravity is, incidentally, a persistent and serious medical concern on Titan. Titan's gravity of 0.14 grams provides the skeleton and musculature with only a fraction of the loading that keeps them healthy on Earth. The human skeleton evolved for 1 gram. It maintains its density through the constant mechanical stress of supporting body weight. Remove that stress, and the skeleton begins to resorb. At 0.14 grams, the loading on the bones is less than 1/7 of what the body is accustomed to. Even with vigorous exercise, bone and muscle loss over an extended Titan stay would be substantial. The long-term health consequences are not fully characterized because no human has ever lived at 0.14 grams for an extended period. We have data on microgravity from the ISS and data on 1 gram from Earth, but 0.14 grams is in between, and the actual trajectory of physiological decline at Titan gravity is, in 2025, an open question. If a human crew survives the first week, survives the first month, begins to think about surviving for a year, the question of resources becomes central. What does Titan actually offer to a civilization trying to sustain itself there? Is there anything on or around Titan that could reduce the burden of constant supply from Earth? The answer is, remarkably, yes. More than almost any other potential human outpost in the solar system beyond Earth, Titan offers usable resources. Nitrogen is the first and most obvious. Titan's atmosphere is 95% nitrogen. Nitrogen is essential for agriculture. It is the primary ingredient of fertilizers, the molecule that makes protein synthesis possible for plants and organisms throughout the food web. Growing food in an enclosed habitat on any off-Earth body requires nitrogen. On the Moon, nitrogen is essentially absent from the surface materials. On Mars, the atmosphere is thin and only about 2.6% nitrogen. On Titan, nitrogen is available in enormous quantities, essentially unlimited. A Titan habitat would have no shortage of nitrogen for agriculture. Hydrogen is the second resource. Titan's atmosphere contains a small but measurable fraction of molecular hydrogen, and the surface materials are rich in hydrogen-containing compounds, particularly liquid methane and ethane. Hydrogen is useful for fuel cells, for reducing oxidation reactions in chemical synthesis, and as a feedstock for producing other chemicals. Electrolysis and chemical reactions that can extract hydrogen from Titan's available compounds are well within the capabilities of a well-equipped outpost. The hydrocarbons themselves are the third resource, and arguably the most extraordinary. Titan's surface contains an almost incomprehensible abundance of organic compounds, hydrocarbons of every length and complexity. The methane lakes are essentially vast reservoirs of potential chemical feedstock. Methane, ethane, propane, acetylene, benzene, these are the raw materials of a substantial portion of terrestrial chemistry and manufacturing. On Earth, these compounds are extracted from petroleum at great environmental cost and processed into plastics, synthetic fibers, pharmaceuticals, and thousands of other products. On Titan, they sit on the surface in liquid form, available for collection and processing. The problem is energy. Converting raw hydrocarbons into useful products requires energy, chemical reactions, catalysts, equipment. A Titan outpost with abundant nuclear power could, in principle, use Titan's hydrocarbon resources to produce polymers for construction, lubricants for machinery, chemical feedstocks for synthesis. This is speculative in its details, but plausible in principle. Titan is not a world with nothing to offer. It is a world with extraordinary raw materials and a crushing energy challenge. Water ice represents the fourth resource. Titan's mountains are made of water ice. Its surface bedrock is water ice. Water is essential for life, for growing food, for electrolysis to produce oxygen and hydrogen. On Titan, water exists, but is frozen in the geology. Melting it requires energy, substantial energy, given how cold the starting temperature is, but the energy is available if nuclear power is adequate. A Titan outpost with sufficient power could melt surface ice, purify it, use it for drinking and agriculture, electrolyze it into oxygen for breathing, and hydrogen for fuel cells or chemical feedstocks. The closed ecological loop that a Titan outpost would need to achieve to become long-term self-sustaining involves producing food from agriculture, recycling water through condensation and filtration, producing oxygen from water electrolysis, managing waste as fertilizer for the agricultural system, and generating power from nuclear sources to run all of the above. None of these individual loops is beyond current or near-future technology. The challenge is integrating them all in a reliable system operating at -179 degrees Celsius on a moon 1.2 billion kilometers from Earth. The question of food deserves its own treatment because it is central to how long a human outpost could sustain itself, and because the answer on Titan is simultaneously more hopeful and more complicated than on almost any other off-world environment. In the short term, there is no question all food comes from Earth. This is the case for any realistic near-term mission to Titan, the same way all food for Antarctic expeditions comes from outside. The supply chain is simply much longer and much more tenuous. A resupply mission to Titan takes years to plan and years to travel. A crew that runs low on food on Titan cannot wait for a supply ship that launches next month. They must either have enough food to sustain them until the next supply window, which might be years away, or they must grow their own. Growing food in space or on other worlds is an active area of research. The ISS has demonstrated the ability to grow small quantities of leafy greens, various lettuces, radishes, mustard greens, in microgravity under artificial light. These experiments are not food production at scale, they are proofs of concept. For a Titan outpost, growing a significant fraction of the crew's caloric needs requires a substantially larger operation. What would an agricultural module on Titan look like? It would be a sealed greenhouse, temperature controlled and heated from Titan's ambient cold to whatever temperature the crops require, typically 15 to 25 degrees Celsius. It would be lit entirely artificially, since Titan's ambient light is far too dim for photosynthesis. The agricultural module would essentially be running an entirely artificial growing environment, powered by nuclear electricity. LED lighting systems, optimized for photosynthesis, are about 40% efficient. They convert 40% of their electrical input into the wavelengths of light that plants actually use. Growing 2,000 kilocalories per person per day of food in an indoor LED-lit system requires on the order of 10 to 20 square meters of growing area per person, depending on crop choice and management intensity, and approximately 1 to 3 kilohertz of electricity per person just for lighting. The crops best suited to a Titan greenhouse are those that produce high caloric density per unit area in short growing cycles. Potatoes, sweet potatoes, wheat, rice, soybeans, leafy vegetables. Potatoes have been extensively studied as a food crop for space because they are dense in calories, grow relatively quickly, and require modest inputs. Soybeans provide protein and fat. Wheat provides carbohydrates. The combination of these staples in a well-managed hydroponic or aeroponic system with nutrient recycling could theoretically support a small crew indefinitely, given adequate power, nitrogen, water, and CO2, all of which Titan provides. The CO2 for plant photosynthesis comes from the crew's exhalations. The nitrogen comes from Titan's atmosphere. The water comes from melted surface ice. The light comes from electricity. The potassium, phosphorus, and trace minerals that plants need come initially from imported fertilizers, but in a long-running system, they would be recycled from human and food waste. The system would need careful chemical management to avoid accumulating toxins and depleting essential nutrients, but in principle, it is a closed system that could run indefinitely. Growing all of a crew's food on Titan would require a significant agricultural module, perhaps 50 to 100 square meters of growing area for a crew of 4 and perhaps 5 kilohertz of additional electrical power. Combined with the habitat's heating and life support demands, the total power budget for a sustainable Titan outpost with its own food production might be in the range of 20 to 30 kilohertz. This is within the capability of a compact fission reactor of the kind that has been demonstrated at the prototype level. A crew that has solved the food problem, that has a functioning agricultural system growing meaningful quantities of food, has taken the longest step toward indefinite survival on Titan. Every other consumable, oxygen, water, power, can in principle be managed from local resources. Food is what requires the most complex and sustained management, and once it is solved, the dependence on Earth resupply shifts from existential to mere logistical. There is something almost meditative about rain on Titan. If you could stand outside in a suit and look up at the orange haze, you would occasionally see methane rain forming. Not like Earth rain, not the rapid drops of liquid water falling through air at roughly 9 meters per second. Titan's lower gravity and denser atmosphere mean that raindrops fall much more slowly. A methane raindrop on Titan falls at roughly 1.5 meters per second, about the speed of a gentle breeze. In low gravity, with substantial atmospheric drag, the drops themselves can be quite large. Some models suggest methane drops on Titan can grow to about 1 centimeter in diameter before falling, compared to a typical Earth raindrop of 2 millimeters. They fall slowly, silently, through amber light, landing on the organic crest of the surface, and either pooling briefly before evaporating or draining into the network of river channels that cut through Titan's landscape. The methane cycle on Titan is not just scientifically interesting, it has practical implications for a human outpost. The rain deposits fresh liquid methane on the surface. Rivers carry it to the polar lakes. Evaporation returns it to the atmosphere. This cycle is not continuous everywhere. Titan's tropics are mostly dry, while the polar regions are wet, in the methane sense. A habitat located near the North Polar Lakes would have access to the most active parts of the methane cycle, which means the most accessible surface liquid, the most atmospheric water vapor equivalents for potential chemistry, and the most dynamic weather to study. The polar regions of Titan, where Cassini observed the greatest concentration of lakes and seas, are where the most interesting things happen and where the resources are most concentrated. Ligeia Mare, the second largest Titanian sea, located at around 79 degrees north latitude, covers an area of about 130,000 square kilometers. Its shores are accessible, relatively flat, carved by the same kind of drainage networks and coastal erosion processes that shape lake shorelines on Earth, but with methane instead of water. A habitat on the shores of Ligeia Mare would be, from a resource perspective, well situated. Liquid methane is immediately accessible for chemical processing. The drainage channels flowing into the sea offer routes for exploration that do not require navigating dunes or climbing mountains. The sea itself could be navigated by boat, a remarkable thought that one day a human crew might sail on a methane sea on a moon of Saturn, and would offer access to bathymetric surveys of an alien lake bed and any organic materials that had settled there over billions of years. Radiation is often cited as one of the primary barriers to long-duration human spaceflight and planetary habitation. On Titan, the situation is measurably better than on many alternatives, but it is not trivial. The primary source of radiation on Titan's surface is cosmic rays, high-energy particles, mostly protons and helium nuclei, that originate from supernovae and other energetic processes throughout the galaxy, and that travel through the solar system at close to the speed of light. Earth's magnetic field and thick atmosphere deflect and absorb most cosmic rays before they reach the surface. Titan has no intrinsic magnetic field, but Saturn's large magnetosphere partially shields the inner portion of Saturn's system, including Titan during parts of its orbit when it is inside the magnetopause. Titan's own atmosphere, while composed primarily of nitrogen rather than the carbon dioxide that makes Mars's atmosphere moderately useful for radiation shielding, is dense enough to absorb and scatter incoming cosmic rays significantly. Measurements from the Huygens probe and from Cassini's instruments suggest that the radiation dose on Titan's surface is roughly 4 to 6 millisieverts per year from galactic cosmic rays. For comparison, the average natural background dose on Earth's surface is about 2.4 millisieverts per year, including radon gas exposure. The radiation dose on the ISS is approximately 50 to 200 millisieverts per year, depending on altitude and solar activity. On the surface of Mars, it is roughly 20 to 30 millisieverts per year. Titan's surface radiation level of 4 to 6 millisieverts per year is elevated compared to Earth, but well below the ISS, and roughly comparable to living at high altitude on Earth, where cosmic ray flux is higher. The radiation dose limit set by NASA for career astronaut exposure is 600 millisieverts for a 10-year career. At Titan's surface radiation levels, a human could remain on Titan's surface for approximately 100 to 150 years before reaching this career limit, meaning that radiation is not, on Titan, the pressing constraint that it is on a deep space voyage or on Mars. This is an important and often overlooked point. The popular image of the outer solar system as a radiation-blasted wasteland does not accurately describe Titan's surface. Titan's combination of thick atmosphere and partial magnetospheric shielding makes it one of the better shielded surface environments in the solar system beyond Earth. The radiation environment is not a major obstacle to long-term habitation. There is a dimension of surviving on Titan that the physics and engineering do not capture: the human dimension. The psychological reality of being on a world 1.2 billion kilometers from everything you know, with no possibility of rapid rescue, with communication delays that make real-time conversation with Earth impossible, with a crew of perhaps 4 to 6 people as the entirety of your social world for years at a time. Researchers studying the psychology of extreme isolation have drawn on data from Antarctic winter overcruise, submarine cruise, long-duration spaceflight, and simulations like Mars 500, a 520-day simulated Mars mission conducted in Moscow in 2010 and 2011. The picture that emerges is complex and sobering. In isolated, confined environments over long durations, humans reliably experience a phenomenon called the third quarter phenomenon, a deterioration in mood, motivation, and interpersonal relations during the third quarter of a mission, followed by a partial recovery in the final quarter as the end approaches. The third quarter of a 10-year Titan mission would arrive roughly 7 years in, long before the end of the mission. Managing psychological health across that kind of duration is not a solved problem. Interpersonal conflicts in isolated small groups are one of the most consistent findings in extreme environment research. NASA research on Antarctic overwinter cruise found that interpersonal tension was a near universal feature of long-duration isolation, usually peaking in the third quarter of the mission. On a Titan mission, where the crew cannot be evacuated, where there is no means of physical escape from a conflict, and where the success of the mission depends on continued effective collaboration, interpersonal conflict is not merely unpleasant, it is operationally dangerous. Sleep disruption is another consistent finding. Titan's day is 15.9 Earth days long. Its sky is dim and orange throughout. There are no strong environmental time cues to synchronize the human circadian rhythm. Without deliberate management of lighting schedules inside the habitat, artificial light mimicking Earth's day-night cycle, crew members' sleep patterns would likely drift out of sync with each other and with themselves, leading to the performance degradation and mood effects of chronic sleep disruption. Sensory monotony is perhaps the subtlest psychological challenge. On Earth, the visual environment is rich, varied, and constantly changing. Different places look different. Weather changes. Seasons change. The built environment provides 1,000 different things to look at. On Titan, the environment outside the habitat windows is, while extraordinary in its way, essentially the same every day. Orange haze, brownish ground, possibly distant lake surface. The same view, day after day, month after month, year after year. Humans are sensory beings, re-evolved in environments of enormous variety. Prolonged sensory monotony produces depression, creativity decline, and a deadening of the capacity for engagement with the world. The mitigation strategies for psychological health on Titan are the same as those studied for long-duration spaceflight. Regular private communication with family and friends on Earth, despite the delay. Diverse recreational activities. Meaningful work that has clear purpose and feedback. Autonomy and agency in mission decisions. Crew selection for psychological stability and compatibility. Access to creative materials, music, literature, entertainment. None of these are exotic. All of them require deliberate provision and management. A Titan mission that attends to psychological health is survivable. One that neglects it is not over the years-long timescales we are discussing. It is worth pausing here and locating Titan explicitly in the broader conversation about where humans might one day live beyond Earth. Because Titan is often overlooked in that conversation, overshadowed by the Moon and Mars, which are closer, better studied, and more frequently discussed in both scientific literature and popular culture. But a serious comparative analysis reveals that Titan, despite its distance, has characteristics that make it in some respects more amenable to long-duration human habitation than either of these closer alternatives. The Moon is the easiest destination in terms of transit time. A human mission to the Moon takes 3 days. The communications delay at lunar distance is 1.3 seconds, effectively negligible. A normal conversation is possible. Resupply missions are feasible on timescales of weeks. Emergency evacuation, while not trivial, is at least conceivable within a matter of days. These logistical advantages are substantial. But the Moon is, in almost every environmental respect, an extraordinarily hostile place for humans. It has no atmosphere. The vacuum means that every pressure vessel must maintain its integrity against zero external pressure. Every surface EVA involves full vacuum exposure. Micrometeorites, which are diverted and burned up in the upper atmosphere before reaching Earth, strike the lunar surface directly. The radiation environment on the lunar surface is severe, approximately 200 to 400 millisieverts per year, depending on solar activity, compared to Titan's 4 to 6. Temperature swings of 300 degrees Celsius between lunar day and night require either careful sighting in permanently shadowed regions or habitats with exceptional thermal management. Water exists on the Moon primarily as ice, in permanently shadowed craters at the poles, concentrated but not abundant, and available in quantities that are not yet precisely characterized. The Moon has nitrogen only in trace amounts, making agriculture difficult without importing it. In summary, the Moon is close and accessible, but it is bare in a way that makes self-sufficiency genuinely difficult. Mars is further, transit times of 6 to 9 months with current or near-future propulsion, communications delays of 3 to 22 minutes depending on orbital positions, but it has characteristics that initially seem more favorable for habitation. Mars has an atmosphere, thin at 0.6% of Earth's sea level pressure but present. It has a day of 24 hours and 37 minutes, close enough to Earth's cycle to limit circadian disruption. It has evidence of extensive past liquid water and probable subsurface ice. Its average surface temperature is negative 60 degrees Celsius, warmer than Titan's negative 179 degrees. It has gravity of 0.38 grams, substantially higher than Titan's 0.14 grams, which reduces the severity of the bone and muscle loss problems. There is significant indigenous carbon dioxide, nitrogen, water, and perchlorate in the Martian soil. The challenges of Mars are different from those of the Moon, and different from Titan's. Mars's thin atmosphere provides almost no thermal insulation and minimal atmospheric pressure. A human on Mars's surface in an unpressurized suit would face boiling blood within seconds, just as on the Moon, because the ambient pressure is too low to keep blood liquid. Full pressurization is required at Mars's surface, the same as on the Moon. The radiation environment on Mars's surface is approximately 20 to 30 millisieverts per year, better than the Moon, but still 4 to 6 times Titan's level, and inadequate for long-duration habitation without supplemental shielding. Dust storms on Mars can last months, reducing solar power generation catastrophically. The Opportunity rover's solar panels were repeatedly covered by dust, and the combination of low light and dust cover has driven the design of nuclear-powered systems for Mars missions. The perchlorates in Martian soil are toxic to humans at concentrations present across the surface, complicating any use of Martian soil for agriculture. When you compare the three environments systematically, the Moon, Mars, and Titan, a surprising picture emerges. The Moon and Mars are closer, but they are bare. Titan is far, but it is rich. The Moon has no atmosphere, no water accessible in quantity, no nitrogen. Mars has a thin atmosphere, some water ice, some nitrogen. Titan has a thick nitrogen atmosphere, enormous liquid hydrocarbon resources, water ice, bedrock, and organic chemistry of extraordinary complexity. Of the three, Titan is the best supplied with the basic materials of life as we know it, even though it requires the most energy to keep a human warm and the most time to reach. This does not mean Titan is the right first choice for human settlement beyond Earth. The transit time alone argues powerfully for Moon or Mars first. But it does mean that the popular dismissal of Titan as too remote, too cold, and too inhospitable to be a serious candidate for human habitation is not supported by a careful comparison. Titan is cold, it is far, but it is not nothing. It is, in many ways, more than either of its competitors. There is a reason that planetary scientists rank Titan as one of the highest priority targets in the search for life in the solar system. And understanding that reason requires understanding something about the chemistry of Titan's surface and atmosphere that goes beyond the basic picture of nitrogen, methane, and cold. Titan's upper atmosphere is constantly bombarded by ultraviolet radiation from the sun, faint given the distance, but present, and by energetic particles from Saturn's magnetosphere. These inputs break apart the nitrogen and methane molecules that dominate the atmosphere and allow them to recombine into more complex molecules. The chemistry is vigorous, specific, and well studied from Cassini data and laboratory experiments reproducing Titan-like conditions. It produces, reliably and continuously, a wide array of organic molecules. The list of molecules detected in Titan's atmosphere is remarkable. Ethylene, acetylene, propylene, benzene, hydrogen cyanide, cyanoacetylene, cyanogen, acrylonitrile, propionitrile. These are not exotic chemicals confined to laboratory curiosities. They are compounds that appear throughout the chemistry of life. Hydrogen cyanide, for example, is one of the key precursors identified in origin of life chemistry on Earth. Under the right conditions, hydrogen cyanide polymerizes into increasingly complex molecules that can include amino acids, the building blocks of proteins, and nucleobases, the building blocks of DNA and RNA. Researchers studying the origin of life have proposed that early Earth's chemistry was enriched by exactly this kind of atmospheric photochemistry, the same basic processes that operate continuously on Titan. The difference on Titan is that these reactions have been running for 4.5 billion years, not in a test tube, not in a laboratory, but across the entire surface and atmosphere of a world the size of a small planet. The result is a layer of tholins, those complex orange-red organic molecules coating Titan's surface to depths that are not fully characterized, but likely measure in the tens of meters or more across much of the globe. When the Huygens probe descended, the sensors detected tholin particles throughout the lower atmosphere. When it landed, it came to rest on a surface enriched in these compounds. The probe's instrument that sampled the surface detected volatilized organics almost immediately. What exactly is in Titan's tholins? Laboratory simulations of Titan atmospheric chemistry have produced tholins containing amino acids when the tholins are mixed with liquid water. Not all 20 amino acids used by life on Earth, but several of them. The significance of this is not that Titan has life. There is no evidence of that. But that Titan's chemistry, under the right conditions, can spontaneously produce the molecular building blocks that terrestrial life uses. The conditions in question include liquid water, which Titan does not have at its surface. But Titan does have interior liquid water. Its subsurface may harbour an ocean of liquid water, kept liquid by tidal heating from Saturn's gravitational pull. The same mechanism that creates the interior ocean of Europa If that subsurface ocean contacts the organic rich surface materials through cryovolcanism or impact mixing, the chemistry of interest could in principle occur. This is the scientific context in which Titan sits. It is not a place we think is probably alive. It is a place we think might be chemically closer to the moment before life appears than anywhere else we can currently reach. Understanding its chemistry in detail, which requires being there, collecting samples, analysing them, would teach us something fundamental about the pathway from chemistry to biology. That is why scientists care about Titan. That is why Dragonfly is going. That is why, eventually, humans might follow. Before any humans go to Titan, a robotic mission is already on its way there. Or rather, it is being built and will be launched in the coming years. NASA's Dragonfly mission, selected in 2019 and currently in development for launch in 2028, with Titan arrival in 2034, is a rotorcraft lander, a drone, essentially, though one of the most sophisticated ever built, designed to fly through Titan's atmosphere and land at multiple sites across the surface. Dragonfly is about the size of a large Mars rover, weighing roughly 450 kilograms, and powered by a multi-mission radioisotope thermoelectric generator. Its rotors, 8 of them in coaxial pairs, are sized for Titan's conditions, where the dense atmosphere and low gravity make powered flight considerably more efficient than on Earth. Dragonfly will fly tens of kilometers between landing sites, sampling Titan's surface at multiple locations with different geological histories, using a mass spectrometer to analyze the chemical composition of surface materials and the lower atmosphere. It will examine the folding-covered plains, the possible cryovolcanic deposits where subsurface water ice might have been brought to the surface by geological activity, and the hydrocarbon dunes. It will characterize the radiation environment at the surface. It will measure atmospheric chemistry with an instrument designed to detect the specific molecules associated with prebiotic chemistry. Over the course of its 3.3-year nominal mission, Dragonfly will fly a total distance of more than 175 kilometers across the surface, roughly equivalent to the entire driving distance of the Curiosity Mars rover in more than a decade. Dragonfly will not find life, almost certainly not, but it will characterize the chemistry of the surface in detail sufficient to understand whether the preconditions for life are present, and if so, of what kind. It will map surface materials across diverse geological units. It will validate models of Titan's methane cycle and atmospheric chemistry that are being built from Cassini data. It will provide the first detailed ground truth measurements of the environment that any future human mission would need to navigate. The data from Dragonfly will be more useful to the architects of a human Titan mission than anything else available. It will identify the safest landing sites, the most accessible resources, the most interesting scientific targets, and the operational challenges of moving through Titan's environment. It will be the foundation on which human mission planning can actually be built, the way Cassini and Huygens were the foundation on which Dragonfly was designed. The history of space exploration is that robots go first. They are cheaper, they are not constrained by life support requirements, they can be lost without catastrophe. Every crewed landing site humans have visited in the solar system, the Moon, was extensively characterized by robotic precursors before the crew arrived. The same pattern will hold for Titan. Dragonfly will go, It will explore. It will report back. And what it finds will shape what comes after. Let us be precise about energy, because energy is the master constraint on everything else we have discussed. Every other problem on Titan, the cold, the darkness, the need for oxygen, the need for food, the need for water, reduces ultimately to energy. With enough energy, you can heat anything. You can electrolyze anything. You can grow food under artificial light. You can melt ice into water. You can maintain a warm, safe, productive habitat on the coldest inhabited surface in the solar system. Without energy, none of it is possible. The energy budget of a Titan outpost has several major components. Heating is the largest. The insulation of even a well-designed habitat is not perfect, and heat leaks out through every surface at a rate determined by the insulation value and the temperature difference. For a 50 cubic meter habitat, well insulated with aerogel composite panels, to a total R value roughly comparable to the best industrial insulation available today. The heat loss to Titan's cold environment might be on the order of 2 to 4 kilohertz continuously. The crew's own metabolic heat, 4 people, each producing roughly 100 watts at rest, more during activity, contributes perhaps 400 watts, offset by the heat absorbed when breathing cold, though the air would be pre-warmed in the habitat. The net heating demand is approximately 2 to 4 kilohertz continuously. Life support, oxygen generation, CO2 scrubbing, humidity management, water recycling requires another 1 to 2 kilohertz. Lighting, if the agricultural module is included, adds 3 to 8 kilohertz, depending on the scale of food production. Communication systems, computing infrastructure, scientific instruments, and general electronics add perhaps another 1 kilohertz. Heating of the water stored aboard requires additional energy, since it must be kept above the melting point of water, 0 degrees Celsius, a full 179 degrees warmer than the outside air. The water storage and distribution system contributes perhaps another 0.5 to 1 kilohertz of heating demand. In total, the electrical power budget for a minimal 4-person Titan outpost, with basic self-sufficiency, producing perhaps 30 to 40% of its caloric needs from on-site agriculture, is approximately 10 to 20 kilohertz, continuous. 24 hours a day, 365 days a year, for a decade, if the crew stays that long. 10 kilohertz for a decade is 876,000 kilohertz hours. At the energy density of uranium, 235 in a typical light water reactor, roughly 45,000 megahertz hours per kilogram, this requires about 20 grams of fissile material. The actual mass of a space reactor, capable of producing 10 kilohertz continuously, including the reactor core, shielding, power conversion system, and heat rejection system, is currently estimated at about 1,000 to 1,500 kilograms, well within the mass budget of a large crewed spacecraft. Plutonium-238 RTGs, the alternative, are simpler and more reliable. No moving parts, no active coaling, no fission control rods, but less power dense. A 10 kHz RTG system would require approximately 15 kilograms of plutonium-238 and might mass 1,500 to 2,000 kilograms in total. The constraint is not mass but plutonium production capacity. At the current rate of US plutonium-238 production, accumulating 15 kilograms would take approximately 30 years. A dedicated industrial expansion of plutonium-238 production could change this, but it requires political and financial commitment. A compact fission reactor is the more scalable solution for a larger or longer duration outpost. The energy stored in a few kilograms of enriched uranium is sufficient to power a Titan habitat for decades, and the mass penalty of the reactor system is a one-time cost at launch. The operational lifetime of a space fission reactor, designed for reliability in an inaccessible environment, might be 10 to 20 years before major maintenance is required. For a permanent settlement, the energy supply becomes even more interesting. Titan's abundant hydrocarbons are a potential long-term fuel source, but using them requires an oxidizer. There is no free oxygen in Titan's environment, unlike on Earth, where hydrocarbons burn in atmospheric oxygen. Water, if obtainable from surface ice in sufficient quantity, can be electrolyzed to produce oxygen, which can then be used to combust methane or ethane in the fuel cell or heat engine. The thermodynamic cycle requires energy to electrolyze water, produces energy in the combustion step, and the net energy balance depends on the efficiency of each stage. It is not a path to net energy production. You do not get more energy from burning Titan's hydrocarbons than you put in to electrolyze the water to get the oxidizer. But in a civilization with abundant nuclear energy, this cycle could serve as an energy storage and distribution mechanism, allowing nuclear electricity to be converted into storable chemical fuel for heating applications or for fueling vehicles. Let us imagine now that all the engineering has been solved well enough. That there is a habitat on Titan, powered by nuclear electricity, heated adequately, growing some food, recycling water and oxygen, with a crew of 4 humans who have been there for several months and are beginning to settle into the rhythms of a Titan existence. What does a year on Titan look like in practice? A year on Titan, in the external sense, is a Titanian year, approximately 29.5 Earth years, but the crew is counting Earth years for their own biological and psychological purposes, because Earth years are calibrated to human biology. 1 Earth year on Titan, 12 months, 365 days. The temperature outside never changes. It is always negative 179 degrees Celsius. The sky is always orange. Saturn is always in roughly the same part of the sky, moving slowly because Titan's orbital period is only 16 days. The seasons on Titan change slowly, almost imperceptibly on a year's timescale, because a Titanian season lasts about 7 Earth years. In 1 Earth year on Titan, you would not notice the seasons changing. You would notice the weather. Titan has weather. Cassini observed methane rainstorms in Titan's tropics, transient brightenings of the surface that appeared after infrequent but intense precipitation events. The polar regions have more regular methane precipitation. Near the northern polar lakes, an Earth year would include variable cloud cover, occasional methane rain, and the gradual evaporation of methane from the lake surfaces into the atmosphere. The weather on Titan is not violent by Earth standards. Winds are light, pressure variations are small, but it is real, varied, and scientifically fascinating. Over a year, the crew would conduct regular EVAs, suited excursions lasting up to 12 hours, to examine the surrounding terrain, collect samples, deploy monitoring instruments, and maintain external equipment. Each EVA would be an extraordinary experience. The orange sky, the low gravity, the dense air through which sound travels strangely, with deeper bass frequencies and slower propagation than on Earth. The biological reality of standing on a world billions of kilometers from home. The science achievable in a year would be transformative. A human scientific team on Titan's surface, with the ability to pick up any rock, drill into any substrate, collect any sample, and analyze it in a well-equipped laboratory, could characterize Titan's surface chemistry to a depth that decades of robotic missions could not match. The organic chemistry of Titan's surface represents perhaps the most complex repository of prebiotic organic molecules in the solar system. Understanding it in detail would illuminate the question of how chemistry becomes biology in ways that earthbound experiments can only approximate. The crew would also, inevitably, struggle. Medical issues would arise, equipment would break. The habitat systems would require maintenance and occasional improvised repair using what the materials were available. Communication with Earth, delayed by 68 to 84 minutes each way, would provide guidance, but not rescue. The crew would need to be capable of solving every problem that arose from within their own resources and expertise. This is the operational reality of a Titan mission, and it is part of why candidate selection for such a crew would be one of the most demanding filtering processes ever applied to human beings. It is easy, in the abstraction of survival calculations and engineering estimates, to forget that Titan is not entirely unknown, that we have been there, that we have sent instruments to its surface, collected data from its atmosphere, mapped its seas and dunes from orbit over a span of 13 years. The history of human exploration of Titan is short, but it is real, and it is worth honouring before we talk about the future. The Pioneer 11 spacecraft flew past Saturn in 1979, providing the first close-up images of the Saturnian system, but not resolving any detail on Titan's surface. The Voyager 1 followed in November 1980, making a close flyby of Titan at a distance of just 6,490 kilometers, close enough to be deflected significantly by Titan's gravity, which actually caused Voyager 1 to exit the solar system in a trajectory tilted 35 degrees out of the ecliptic plane. The trajectory was deliberate. Mission planners chose the close Titan flyby over a Neptune encounter that would otherwise have been possible because Titan was considered the highest priority scientific target in the outer solar system. The Titan flyby ended Voyager 1's planetary mission, but gave scientists their first detailed atmospheric data. What they found: a thick nitrogen atmosphere, methane chemistry, temperatures consistent with complex organic chemistry, made Titan even more fascinating and set the scientific agenda for the next generation of missions. The Cassini-Huygens mission, a joint project of NASA and the European Space Agency, launched in October 1997 and arrived at Saturn in July 2004, represented the largest and most complex planetary mission ever attempted at the time. Cassini was a spacecraft the size of a school bus, carrying 12 science instruments, powered by 3 RTGs, producing a total of 887 watts at launch. It orbited Saturn for 13 years, making 127 targeted flybys of Titan, in addition to hundreds of more distant observations. The data it returned transformed our understanding of Titan from a mysterious orange ball to a detailed world. The Huygens probe, released from Cassini in December 22nd and arriving at Titan on January 14th, 2075, was the most distant landing of a human-built object on another world ever achieved at the time. It parachuted for 2 hours and 27 minutes, returning data on atmospheric composition, temperature, pressure, wind speed, and electrical activity throughout its descent. Its cameras captured images of drainage channels, a bright highland with river systems, and a dark lowland plain littered with rounded pebbles of water ice. The landing site, later named for the probe itself, is located at about 10 degrees south latitude on what appears to be a broad flat plain. The surface beneath the probe, measured by acoustic sensors, was described as having a consistency similar to wet sand or clay, soft enough to compress slightly under the probe's weight. The last temperature measurement before transmission ended showed the surface temperature was negative 179.2 degrees Celsius. When Cassini's mission ended in September 2017, deliberately plunged into Saturn's atmosphere to prevent contaminating Titan or Enceladus with terrestrial bacteria, it had accumulated 635 gigabytes of data. It had mapped Titan's North Polar lakes in detail, discovering that the largest, Kraken Mare, is connected to Ligeia Mare by a narrow strait that Cassini scientists named the Throat of Kraken. It had observed weather patterns, including large methane cloud systems, and watched seasonal changes as Titan moved from northern winter to northern spring and summer during the mission's 13-year duration. It had measured the composition of the upper atmosphere with a mass spectrometer and identified hundreds of organic molecules, some of them of extraordinary complexity. It had detected the infrared glow of Titan's surface in cloud-free windows in the haze, producing the first surface maps. This is the foundation. Not speculation. Not hope. Data. Hard-won, instrument-measured, mission-tested data from probes built by human engineers, launched by human rockets, operated by human scientists over decades of their professional lives. The next chapter is robotic. Dragonfly. The chapter after that, if we choose to write it, involves human hands. The final rung of the ladder is the most ambitious and the most uncertain. Permanent human settlement on Titan. Not a mission, not an expedition. A settlement. People who go to Titan and do not come back. You build a community there, who have children, who raise subsequent generations on a world of orange skies and methane seas and ancient organic chemistry. This is, in 2025, purely speculative. But speculative is not the same as impossible, and the question of whether Titan could support permanent human habitation is a question worth taking seriously, because it probes the actual limits of what Titan and human biology can sustain together. The first challenge to permanence is the biological problem of reproduction and child development in low gravity. No human has ever been born or raised in gravity significantly different from Earth's 1 gram. We do not know what happens to fetal development, birth, infant bone and muscle development, or childhood growth in 0.14 grams. The skeletal system develops in response to mechanical loading throughout childhood and adolescence. In 0.14 grams, those loading signals are reduced by almost an order of magnitude from what the human body evolved to require. Would a child born and raised on Titan develop a normal skeleton, a normal musculature, a normal cardiovascular system? We do not know, and the ethical barriers to conducting the experiments that would produce the data are both substantial and appropriate. Speculative physiologists have suggested that humans raised in low gravity might develop differently, but not necessarily pathologically. Lighter bones, reduced muscle mass, but functional health in their actual environment. But such people would be unable to return to Earth without catastrophic consequences. Their bones and cardiovascular systems would not tolerate 1 gram. They would be Titanian in a literal physiological sense, unable to live anywhere else. There would be the first generation of humans who are not, in the full biological sense, Earthlings. This is a transition point so significant that it is difficult to overstate it. The children born on Titan would represent the first humans for whom Earth is not a possible home, the first humans whose biology has diverged from the ancestral template in a way that is tied to their world rather than to a choice or an accident. They would be Titanians, a new kind of human being. The second challenge to permanence is genetic diversity. A small founding population faces inbreeding risks on a timescale of generations. Genetic diversity requires either a large founding population, which enormously increases the mission's cost and complexity, or a mechanism for maintaining genetic exchange with Earth, which requires either physical travel or the use of stored gametes and embryos to introduce new genetic lines. Stored genetic material could, in principle, be maintained and used over long timescales, but the biological, ethical, and social dimensions of this are not simple. The third challenge is cultural. Permanent settlers on Titan would be geographically and communicatively isolated from Earth in a way no human community has ever experienced. An Antarctic base is remote, but it is on the same planet. It is accessible by aircraft in emergencies. Its inhabitants can return home within days if necessary. Titan is years away. The communication delay makes anything like cultural continuity with Earth impossible to maintain in real time. Titanian settlers would develop their own culture, their own traditions, their own relationship to their world, diverging from Earth's culture over generations. Whether this divergence is a tragedy or an adventure, or simply a fact, depends entirely on your values. From one perspective, it represents the loss of human connection, the severing of a community from its roots, the loneliness of the outermost frontier. From another perspective, it represents the most extraordinary expansion of human experience in history, the creation of a new form of human civilization in a world utterly unlike anything our ancestors ever imagined. But built from the same atoms and driven by the same curiosity that built every civilization before it. We have been building a ladder. Let us now stand back and look at the full structure. Unprotected, a human on Titan's surface survives roughly 15 seconds to 2 minutes. This is not survival in any meaningful sense. This is simply the interval between arrival and death. In a basic thermal and respiratory suit, with adequate oxygen and heating, a human can survive on Titan for approximately 8 to 12 hours per excursion, limited by oxygen supply and battery life. Repeated over multiple excursions, with returns to a pressurized vehicle or habitat between each, this extends indefinitely as long as consumables are replenished. In a properly designed habitat with nuclear power, adequate insulation, imported food and water, and a functioning life support system, a human crew can survive on Titan for months to years. This is the state of technology that, with significant investment in development, could be achieved within the next 50 to 100 years. The physics allows it. The engineering is hard, but not fantastical. The obstacles are logistical and financial rather than fundamental. With in situ resource utilization, melting surface ice for water, extracting nitrogen from the atmosphere for agriculture, largely built from massive testing, a patient that can be equipped by human bodies. And at the outermost edge of speculation, with multi-generational commitment, with genetic management, with the development of a Titanian culture and biology, humans could potentially live on Titan permanently, in the sense that their descendants could continue to live there after the founders are gone, adapted physiologically and culturally to a world of orange skies and methane seas and the distant pale disk of a sun that gives 1/100th the light of what we know on Earth. Each rung of this ladder is a different answer to the question. Each one is true at its own level of technology and commitment. The question is not which answer is right. They are all right. The question is, which level of commitment is worth making, and what we value enough to pay that price. There is a question that hovers over any discussion of human survival on Titan, over any serious conversation about life in the outer solar system. That is worth addressing directly, because it shapes the entire context of why any of this matters. It is the question that Enrico Fermi reportedly asked at a lunch conversation in 1950, in a formulation deceptively simple enough to fit on a napkin. If the conditions for life are this widespread, if a moon of Saturn in our own solar system has the organic chemistry needed to produce the building blocks of biology, if that chemistry has been running for 4.5 billion years, if this same basic photochemistry of nitrogen and methane and ultraviolet light must be occurring on similar worlds throughout the galaxy, then where is everybody? If life arises wherever conditions permit, and if the conditions permitting it are this widely distributed, shouldn't the galaxy be full of civilizations? Shouldn't we have evidence of them by now? We don't. Not confirmed, unambiguous, universally accepted evidence. The radio silence of the universe remains one of the deepest puzzles in science. Titan doesn't resolve the Fermi paradox, but it sharpens it. If the building blocks of life are available on a frozen moon, 1.2 billion kilometers from the Sun, in a solar system whose star is a perfectly ordinary G-type dwarf in the outer arm of a perfectly ordinary spiral galaxy, in a universe containing 100 billion galaxies, each containing 100 billion stars, then the raw materials for life are essentially everywhere. They are not rare, they are abundant. The organic molecules that Cassini measured in Titan's atmosphere are not exotic. They are the common products of nitrogen, methane, and ultraviolet light, three of the most common things in the universe, interacting. And yet, here we are. Alone, so far as we can determine, on a planet in a solar system that has at least two worlds, Earth and Titan, with significant organic chemistry, and possibly more in the form of Enceladus's subsurface ocean with its detected organic plumes, Europa's ice-covered ocean, and the ancient lake beds of Mars. The solar system is full of chemistry. Whether it is full of life is a question we cannot yet answer. What exploring Titan brings us, beyond the science of that specific world, is a data point, a test case. If Dragonfly finds evidence of active chemistry in the organic surface materials, consistent with biological processes, that is one kind of answer. If it finds only pure abiotic chemistry, extraordinarily complex, but devoid of the patterns associated with life, that is another kind of answer. Either result will be among the most significant scientific findings in history, because either result will constrain what we believe about the distribution of life in the universe. A human presence on Titan could take that investigation to a depth no robot can achieve. We know that this is more. A scientist standing on Titan's surface, with the full sensory apparatus of a trained human mind, with the ability to make real-time decisions about what to examine and how, with access to a well-equipped laboratory to analyze what they find, could characterize Titan's surface chemistry in a year to a depth that robotic missions might take decades to achieve. The difference between robot and human exploration is not just speed. It is the irreplaceable capacity of a human mind to recognize the unexpected, to follow an intuition to an unpredicted finding, to see the thing that no one knew to look for until they were standing in front of it. This is what the history of exploration consistently shows. Columbus did not find North America because he was following a pre-programmed route designed to encounter it. Lewis and Clark did not catalogue the Shoshone people or the Rocky Mountain passes or the Columbia River Basin because a robotic precursor had already told them exactly where to look. The great findings in the history of exploration have almost always come from the capacity of human minds to respond to what was actually there, not to what was predicted. Titan is waiting for exactly this kind of encounter. Its surface chemistry is complex enough that we do not know what we will find when we look closely. It has been sitting there, accumulating organic compounds from the sky, for longer then the Earth has had complex multicellular life. What is in those tholins? What is in the bottom of Ligeia Mare? What is in the subsurface, where tidal heating from Saturn might be keeping a layer of ice-water chemistry at a temperature above freezing, mixing with the organic material that has been filtering down from above for geological ages? We do not know, and we will not know until we go. The question, how long could humans survive on Titan, sounds like a survival challenge, like a question from a wilderness training course, scaled up to the solar system. Bring the right gear, stay warm, keep breathing, don't run out of food, and you survive. Scale up the gear, extend the supply chain, and you survive longer. But worked through carefully, honestly, with the real numbers in front of you, rather than rounded comfortably down, the question turns out to be something else. It turns out to be a question about the boundaries of what our species is and what it could become. The boundary at the bottom is absolute and physical. Without insulation and oxygen, you die in under 2 minutes. This is not a challenge. It is a wall. The wall is made of thermodynamics and biology, and it does not negotiate. Above that wall, the question becomes engineering. How good is the insulation? How reliable is the oxygen supply? How capable is the power system? These are not questions with single right answers. They are questions that engineering can answer at different levels of ambition, different points on the curve that runs from what we can do today to what we might build in 50 years or 100 years. Every advance along that curve represents more time, more safety, more capability on Titan's surface. But above the engineering, above the suits and habitats and nuclear reactors and aerogel insulation and closed-loop life support, the question becomes something else entirely. It becomes a question about whether human beings can make a world their home that is not the world they came from. Whether the drive to explore and inhabit is stronger than the cold. Whether the curiosity that makes us ask the question in the first place is strong enough to actually answer it with our feet on the ground, our lungs breathing recycled air, our eyes looking out at an amber sky through thick triple glazed windows at negative 179 degrees outside. The evidence from history is that yes, it is strong enough. It has always been strong enough. Human beings have died in the pursuit of geographic knowledge in numbers that, taken individually, are tragedies, and taken collectively, are an argument for the depth and persistence of this drive. The Antarctic expeditions of the early 20th century lost people and still came back. The early aviation pioneers died and others still flew. The early spaceflight programs lost crews and continued. Each loss is a tragedy. The continuation is also a fact. Titan is not the moon. It is not Mars. It is not even close in the logistical sense. It is 1.2 billion kilometers from Earth, years away by any trajectory we can currently calculate. A mission to Titan is not a mission that anyone living right now will go on. It is a mission for the second half of this century, or the first half of the next. For people who are children now, or not yet born. For a generation that will inherit the technology and the political will and the scientific understanding that we are building today, with missions like Dragonfly and with theoretical work like this. But the question they will be answering is the same one being asked right now. How long can we survive there? What does it require? Is it worth what it costs? The answer to the last question is not in the physics. The physics tells you the cost. The worth is a human judgment. And human judgments about whether exploration is worth its cost have, through the entire history of this species, consistently and repeatedly come down on the side of going. The methane rain is falling on Titan right now, somewhere near the North Polar Sea, slow drops, drifting down through amber haze onto organic ground that has been accumulating chemistry for billions of years. Saturn is in the sky. The temperature is negative 179 degrees Celsius. Nobody is there, not yet. There is a moment in the history of any great exploration when the question stops being purely technical, when it stops being about supplies and insulation and radiation doses and propulsion systems and becomes something else, something older, something that sounds, if you say it plainly, almost embarrassingly simple. Why? Why would anyone go to Titan? Why would any civilization invest the staggering resources required, the decades of development, the political will, the engineering talent, the human lives, in sending people to a moon of Saturn where the temperature is negative 179 degrees Celsius and the rain is made of liquid methane and the sun is a dim pale coin in an orange sky? The answer is not simple, and it is not single, but at its core, I think it is this. Because Titan is the place in the solar system where the chemistry that might precede life is most abundant, most complex, most accessible, and most unlike Earth. Understanding Titan is not just an exercise in planetary science. It is a window into the question of how chemistry becomes biology, of whether the processes that produce life on Earth are common throughout the universe, or whether they are a specific and rare accident of Earth's particular circumstances. Titan does not answer this question. It puts the question in sharper focus than it has ever been in before. There is also the simpler, and perhaps more honest reason: exploration. The same drive that sent people across the Atlantic in wooden ships, across the Pacific in outrigger canoes, to the poles of Earth in blizzards and frostbite and extraordinary hardship. The drive to see what is on the other side, to stand where no one has stood, to know what is there. Titan, with its methane seas and organic dunes and ancient chemistry, and Saturn hanging vast and banded overhead, is among the most astonishing landscapes available to us in this solar system. The desire to stand there, to look at it with human eyes, to touch it with gloved human hands, to bring back to Earth the sensory reality of what it is like to be on a world like that, is not irrational. It is one of the most characteristically human things there is. The Huygens probe, which landed on Titan in 2005, transmitted data from the surface for 72 minutes. In those 72 minutes, it sent back the first direct data ever received from Titan's surface: temperature, pressure, atmosphere composition, images of a pebble-strewn terrain. Then, the relay link was lost, and the data stopped. Huygens is still there, a small aluminum and titanium artifact of human curiosity sitting on the surface of Titan in the cold and the dark, 1.2 billion kilometers from the hands that built it. In a world of methane and fullenes, an ancient organic chemistry that it explored for 72 minutes and then became part of. We have been to Titan. Not with human hands, but with human minds, human engineering, human curiosity, reaching out across the solar system at the speed of light in radio waves, and arriving through 20 years of travel and effort at a rain-swept organic landscape on the edge of a methane sea. The next step is harder. The step after that, harder still. Each step requires technology we do not yet have, resolve we have not yet demonstrated, commitment we have not yet made. But the physics does not forbid any of them. The laws of thermodynamics do not prohibit warming a habitat to habitable temperature. The laws of chemistry do not prohibit growing food in nitrogen under artificial light. The laws of biology do not prohibit human beings living for years in a world of 0.14 grams, though they will change them. What the physics does require is honesty. An honest accounting of the energy budget, an honest reckoning with the cold, an honest acknowledgement that the distance is not a detail to be waved away, but a central, defining feature of what a Titan mission is. You are not going somewhere and coming back next month. You are going somewhere and spending years there, changing the way you experience time, changing the way you relate to Earth, possibly changing the way your body works, certainly changing the way you understand the universe. The question of how long humans could survive on Titan does not have a single answer, because survival is not a single thing. It is a spectrum, from the seconds of an unprotected person in the cold to the generations of a permanent civilization that has made a world its own. The physics constrains the bottom of that spectrum, absolutely. You cannot survive on Titan without insulation, without oxygen, without power. The engineering defines the middle. With current technology pushed hard, you can survive for years. The limits of biology and human commitment define the top. With everything we might become, you can survive on Titan indefinitely. The question asks about limits, but what it really reveals is a staircase. A staircase from where we are now to places we cannot yet fully imagine, built one engineering challenge at a time, one mission at a time, one generation at a time, out toward a world where the rain is methane and the mountains are ice and the sky is the colour of ancient amber. That staircase goes as far as we are willing to build it. The physics lets it go the distance. What it takes is us. Let us close by imagining the view. Not the engineering, not the biology, not the survival calculations, just the view. You are standing on the surface of Titan. You are in a suit, insulated, oxygen-fed, heated, sealed against the nitrogen methane air outside. Through the visor, the world is amber. The sky above is orange-brown, lightening a little toward zenith, where the haze is thinnest, darkening toward the horizon, where the atmosphere path length is greatest. There are no stars visible. The haze scatters all direct starlight into a uniform glow. The ground beneath your boots is dark brownish red, the colour of dried tobacco, coated in a fine layer of organic material that has been falling from the upper atmosphere for billions of years. It crunches slightly as you walk, or does not crunch. You cannot hear it through the suit, but you feel the slight resistance. The soil, if you can call it that, is a mixture of water, ice and organic compounds. And under its surface at some depth is the bedrock of water ice that forms the geological foundation of this world. In the direction of the sea, there is a shimmer, Ligia Mar, vast and still, its surface reflecting the amber sky. It does not look like water. It is darker, more opaque at certain angles, less reflective. It is liquid methane mixed with ethane at negative 179 degrees Celsius. Waves, if there are any, would be tiny. Titan's low gravity and light winds produce ripples rather than swells. The shoreline is jagged and carved, like a shoreline eroded by ice and chemical dissolution, which is exactly what it is. Above the sea, clouds, not white cumulus, dark methane clouds, irregular, moving slowly in the light winds. Occasionally, at the limit of what your visor can detect, a slightly darker streak, rain, falling slowly, gently, in long curved trajectories modified by the wind. And above everything, to one side of the sky, Saturn. Enormous. A pale tan disk with the faint lines of its cloud bands visible even through the haze. The rings, at whatever inclination this season brings, stretching in an arc of pale light. In this moment, in this place, Saturn does not look like an astronomical photograph. It looks like a physical thing, a thing you could fly to in an appropriate vehicle. A thing that has mass and gravity and weather of its own, right there above you, dominating a quarter of the sky. You have been standing here for 12 minutes. You have another 7 hours of EVA time before your suit needs to return. 7 hours on Titan. 7 hours on a world where it rains methane and the mountains are ice and the rivers run with hydrocarbons and the sky is amber and Saturn watches everything from above. There are places in the solar system that are hostile, that offer nothing, that would kill you and offer nothing in return. Titan is not one of them. Titan is extraordinary. Titan is a world. It has weather and seasons and lakes and rivers and an organic chemistry of staggering complexity. It has gravity, light, pressure, atmosphere. It has, in its own alien way, everything that a world needs to be a world. It will kill you if you are unprepared. It will kill you quickly and without ceremony if you arrive without insulation, without oxygen, without power. But it will shelter you, sustain you, reward you, with one of the most remarkable views available to human eyes, if you arrive with what it demands. What it demands is not much, in the cosmic sense. It demands that you take the cold seriously, that you account for the darkness, that you plan for the distance, that you bring enough power to stay warm, enough oxygen to stay alive, enough food to stay fed, enough will to stay on. The cold is negative 179 degrees Celsius. The sky is amber. The rain is methane. The nearest other human beings you could reach in under a year are 1.2 billion kilometers away. And Saturn is right there, hanging in the sky, banded and magnificent, and indifferent in the way that all massive ancient things are indifferent. It was here before you arrived. It will be here long after any expedition you are part of has ended. It watched the organic compounds fall from the upper atmosphere for 4.5 billion years before you arrived. It will watch them fall for billions more. You have 7 hours. The surface is just ahead of you. The sea is to your left. The habitat is behind you, a small, warm, lighted point in the amber landscape. What do? You walk forward. That is what humans do. You walk forward into the world in front of you, and you see what is there. That is what we have always done. From the first footstep onto an unfamiliar shore, to the last step down the ladder of a lunar lander onto the grey dust of the moon, to whatever comes next. That is what survives. Not the body, not necessarily, not forever. The curiosity, the walking forward, the need to see what is ahead. On Titan, what is ahead is everything. An entire world, ancient and complex and alive in its chemistry, if not in its biology, waiting. The rain falls slowly in the amber air. The methane sea reflects the pale disk of Saturn. The dunes stretch to the horizon, shaped by 1 billion years of wind. Nobody has ever been here before. And the universe offers this moment to exactly one species that has figured out, through physics and engineering and extraordinary effort and a refusal to accept that the solar system is not for them, how to get here and how to stay. How long could humans survive on Titan? As long as they bring what the cold demands. As long as they remember what the distance means. As long as they keep walking forward. Which, if the last several 100,000 years of human history are any guide, is a very long time indeed.